Hi, my name is Gareth. Welcome to this introductory talk about simultaneous localization and mapping, or SLAM as it is often abbreviated. This talk is intended as a high-level introduction. We're going to give an overview of what SLAM is, investigate a conventional visual SLAM pipeline as used with computer vision, and then look at some high-level design trade-offs that you might encounter in a SLAM problem. So what do we mean by SLAM? So SLAM refers to a two-step process whereby we must simultaneously localize and map. By localization, we mean recovering the state of a vehicle or a sensor platform, usually over multiple time steps. So for example, you might be interested in the position and velocity of your drone, or in the position and orientation of your AR headset or of a cellular device in the case of a mobile AR application. And in the process of doing so, you typically have to build a map that is recovering locations of some landmarks in a common reference frame. You need the map to compute your location, and you need your location in order to build the map. And so this process has to happen simultaneously. And that's what SLAM is doing at a high level, is iteratively recovering these two quantities. Now, you could argue that we've been doing this for a very long time. For example, early sailors could navigate the Mediterranean by adhering to coastal waters and recognizing specific recognizable visual landmarks as they sailed. So as you move, you can imagine identifying landmarks you know on the coastline, and then from that you can get a sense of how you're moving, and then as you move, add new landmarks to your mental map. Of course, this is prior to the innovation of astral navigation using the stars. So the process of accumulating that knowledge is the mapping step, and then the task of recognizing where you are using that knowledge is the localization step. I like this map here. It's an early map of the world developed by Eratosthenes. It reflects kind of an interesting property in SLAM and state estimation, which is that where more data is available, the accuracy is generally going to improve. So from this map, as you might imagine, most of his data was collected around the Mediterranean, and that's where the map is the highest quality. Elsewhere, of course, it looks a lot more approximate. So technology has improved a lot over time by orders of magnitude, in fact. So this visualization is a 3D reconstruction of Rome, built from tens of thousands of images using a process called structure from motion, and we're going to come back to what that is in a little bit. But for now, all you need to know is that these red triangles reflect the positions and view angles of camera images, presumably captured by tourists. And then the points are 3D points that we have triangulated with those cameras in order to build a high-level or a high-quality reconstruction. So this kind of technique, it can actually map the scale at we can map the world at a scale of centimeters or even better, and it can also scale from very small problems, like a few photographs on a cell phone, to massive problems at city scale, like this one here. And you can actually see the same property reflected in this map as in the previous one, which is that where the data is most dense, presumably by the Colosseum, since people will photograph it the most frequently, the map is very dense and very high quality, and then elsewhere it is not. So while you wouldn't typically run that kind of algorithm on an embedded system, we do run a very, very similar algorithm on the Skydio drone called visual inertial odometry. And we'll come back to what that is exactly towards the end of the presentation. But at a high level, what we're doing is we're associating points over time in an image. That's the green traces you can see on the video on the right. Those green traces reflect feature tracks. That's a point that we've identified in a sequence of images over frames. And then using some basic 3D geometry, we can turn those 2D feature tracks into a 3D point cloud and a 3D estimate of where the camera is. And that's what you see happening on the left video. And you'll note that this point cloud is considerably more sparse, considerably smaller than the visualization of Rome I showed on the last slide. And that's because we're operating on a computationally constrained platform. We don't have much room to optimize a large data set, but also we're only interested really in recovering the motion of the drone. And so we don't need to build a very high quality or large point cloud in order to do that. But the underlying algorithm is very similar. So what is SLAM as compared to just plain localization? I think this is worth touching on briefly. So the image you see on the left is of a GPS constellation. In the case of GPS localization, the map is known a priori because the satellite orbits are deterministic and can be modeled ahead of time. And so you don't need to build the map online, at least at the receiver level. You need only solve for the position of the receiver given the measurements from the satellites. And so this is just a plain localization problem. Similarly, on the right, we have the Skydio drone being calibrated in the factory. The robot arm is moving it around, and there's a fiducial target underneath it. The fiducial target features many different AR tags or April tags. And the relative position of all those April tags is known a priori as well. So the map is sort of given, and you can reduce it to a plain localization problem in that case. So when we talk about SLAM, we're really talking about the joint process of having to solve for both quantities, both the map and the ego motion of the sensor platform at the same time, since both are initially unknown. So to formulate a SLAM problem, you need a few key ingredients. One of the first ones is sensor data, of course. And the choice of sensor data and sensor modality is quite important because ultimately it's going to drive many of your design considerations in the estimator that you build. So some choices are exemplified here. This list is by no means exhaustive. Some additional things you might include are GPS sensors, magnetometers, maybe wheel encoders on a wheeled vehicle. Arguably the lightest weight choice, and the one that I have the most experience with certainly, is cameras and inertial measurement units. These are appealing because they are relatively inexpensive, small, light, fairly straightforward to integrate, low power, and you can generate fairly high quality reconstructions with them with recent advancements in computer vision. Certainly not the only choice, but the one that we'll focus on the most in this presentation. So the second part in formulating a SLAM problem, you need some states that you want to recover using your sensor data. So two of these we've already discussed. One is the ego motion of the robot, which could be its position, velocity, rotation, for example. Typically, you'll have many of these over time since the system is kind of evolving and moving over time. And then you'll have a 3D map. And there's many different ways to parameterize the map, and we'll touch on some of those. But it will be driven by computational considerations. Potentially, if you need a high-quality map as a byproduct of your algorithm, that will influence the choice of map. And then lastly, they're the calibration parameters, and these are less obvious than the first two why you might care about them, but they are nonetheless important because every sensor that you add is going to have some kind of scale and bias associated with it. And so you need to consider those as well if you want to have a high-fidelity model of the world. So every sensor that you add is going to have some sensor measurement model associated with it, and that's what we've written here. We've kind of wrapped it all up in this opaque function h, but h is a function, usually some nonlinear function of the states that you care about, like the ego motion of the sensor platform, the map parameterization, and the calibration parameters, and the function h outputs the sensor output. And so it's this model that relates what your sensor gives you to all the quantities that you care about estimating. And without this, you can't recover those quantities. You need some kind of underlying model that relates the two things. So in very, very simple cases, this function h might be trivially invertible, and you can invert it and give the inverted function the sensor output and recover the parameters that you care about, but that's usually not going to be the case. Usually you're going to have a bunch of different sensor models for different measurements, and they will comprise a nonlinear set of equations, and you need to solve that nonlinear set of equations in order to recover some parameters. And that's effectively what the SLAM system is typically doing. And there are many different ways to set this up, but it is usually the case that the implementation complexity and the computational cost will increase with the complexity of the sensor measurement model and the number of measurements. So that will also be a design trade-off that you have to think about. How many sensor measurements do you want to use? How many sensors do you want to add? And how complicated are those sensors? Because all of them will increase the computational cost potentially. So as some specific examples, let's look at calibration, a problem which is near and dear to my heart. So these are some examples I picked. Let's say, for instance, that you are working on an autonomous vehicle. You might consider adding wheel odometry as a sensor in your SLAM pipeline. So the wheel odometer basically is going to count revolutions of the wheel and then give you an estimate of how far you've traveled based on those revolutions. But that's subject to assumptions about the physical world, like the radius of the tire, for instance. And so if you were to incorporate that in your SLAM pipeline, you might wish to treat the radius of the tire or the pressure of the tire perhaps as a calibration parameter you need to estimate. So the addition of that sensor has added another parameter that you have to reason about. Similarly, the example we have in the middle here, this is a visual inertial device. It has cameras, it has an IMU, and they're on the same PCB. And even though you lay out that PCB very precisely in CAD, Small variations in manufacturing in the SMT process, for example, can introduce misalignment between the sensors, between the IMU and the camera. And then that will become an error later in your SLAM pipeline unless you account for it and estimate that transformation. And then lastly, on the right, there's a little video sequence here looping of a Skydio camera sensor that is being subjected to a temperature sweep. And though the effect is subtle, you can see that the image is expanding and compressing as we subject the camera to the sensor, to the temperature sweep. So as the lens changes with temperature, so must how we model it in that system of equations. And lastly, the last piece, but certainly not the least important piece of our sensor measurement model is the noise. So all sensors exhibit some minimum amount of noise. That's just a physical reality. Noise is a random process that you can only model via statistical means. It's a random error that is uncorrelated with your state. You can reduce the effect of noise by adding more measurements, but you can never really eliminate it. And it's worth distinguishing between noise and model error. Model error is an error in your model that is introduced from limitations in your sensor model. So perhaps you assumed a simplified physical model of the world, or maybe you omitted a calibration parameter that you should have considered. But those types of errors will be correlated with the state usually. The takeaway here is even if you eliminate those and build the most kind of comprehensive, complete, and accurate model you can, there's always going to be uncertainty resulting from the noise. So SLAM is a kind of fundamentally uncertain process in that sense. You can mitigate it somewhat by collecting more data, but you can never truly eliminate it. And then lastly, we have the choice of the map. So there's many different ways you can go here. It's going to depend on the type of sensor data you have. It's going to depend on the level of fidelity that you need, but there's many different ways to set up the map. For instance, if you have a collection of large photographs spanning a large area, a sparse point cloud might be very suitable because it would allow you to capture the bulk geometry of the scene and recover a coarse reconstruction without using very much data because the point cloud is sparse. On the flip side, if you're doing motion planning on a robot, you likely need a dense map for collision checking. And so in that case, you might choose a voxel map or a truncated sign distance function like the image on the right here. So there's many different choices. They're each going to have computational trade-offs and are going to have to be driven by the design considerations of your system. So what I'm trying to drive home here is that there are a bunch of different axes that you have to think about when parameterizing a SLAM problem. It's not just the math underlying the system itself, it's the whole pipeline and how holistically you have to think about what sensors you're using, what quality they are, and how they fit into your product, and then what the downstream considerations of that are going to be in the SLAM problem itself. So this graph is kind of simplistic, but I think it captures the high-level trade-offs you might be confronted with. Adding more sensors might reduce the total amount of error in your solution, but it will have some physical cost, it will have computational cost. Similarly, buying a cheaper sensor might reduce the physical cost, but of course, there may be more error in the solution as a result. So you have to consider these different trade-offs when you're setting up a product that is going to contain a SLAM system. So before proceeding, I want to talk quickly about factor graphs. The reason I think these are worth touching on is that if you refer to the SLAM literature, you're going to see them over and over again in a bunch of different places. So having some kind of understanding of what they are is important, I think. Factor graphs basically allow you to graphically represent your SLAM problem. So nodes in the factor graph are states that you care about, things like your map or the ego motion or the calibration parameters, and then edges are measurements that relate those different nodes. So for instance, you may have many different sensors, and not every sensor is going to touch every single parameter in your big set of sensor measurement models. So the graph essentially encodes this sparsity. It relates which parameters are in contact with other parameters because they are touched by some shared sensor measurement. And so you can have unary and binary and ternary and so on factors depending on the complexity of the sensor measurement models themselves. And there's a convenient mapping from the factor graph to the to your set of sensor measurements. So here we have a system of equations. Typically it'll be a nonlinear set of equations coming from your different sensor measurements and your different sensor models. And then the factor graph itself basically captures how different parameters are connected to each other via those different sensor measurements. And so it's a visual representation of that system set of equations, and it captures the sparsity that is kind of inherent in a lot of SLAM problems, as we'll see. So with all that said, let's look at a real-world example. The The example I've chosen here is bundle adjustment. The reason I've chosen it is it kind of represents the state of the art in Visual SLAM. It's highly scalable, it's adaptable to embedded systems, and has had pretty good success, I would say, as applied in industry. The high-level problem with bundle adjustment is we're going to parameterize the world or our map as a set of 3D points, like that sparse point cloud of Rome that I illustrated earlier. You're going to represent the pose of the camera as a series of positions and rotations of that camera in space. And then we're going to try and solve for both of those quantities. And the reason it's called bundle adjustment is that each point that you're trying to estimate has a whole set of rays passing through it. And those rays emanate from where the point was observed in a camera image out into the 3D world. And if you intersect that whole bundle of rays, you can triangulate a given 3D point. And similarly, if you have a bunch of 3D points in your map and observations of those points in a camera image, you can do the inverse triangulation and solve for the camera pose given the intersection of those rays. And so bundle adjustment, effectively what it is doing is it's an optimization problem where we are iteratively doing these two things, solving for the pose of 3D points in the world given observations of them in images, and then solving for the pose of cameras given our 3D map and observations of those points in the camera images. And it turns out this algorithm can be made highly scalable and can be made quite accurate. And so it's very effective in embedded systems, or you can scale it all the way up and do full city scale style reconstruction. One thing that's important to note here is that we have introduced an abstraction in the sensor model, which is that we are now treating the input to the algorithm as these associations in the images. So we have these 2D feature locations in each image, and we're treating that as the readout from our sensor, when in fact what the sensor actually gave us was a camera image. We're going to abstract that away, though, and say that what we have is a collection of 2D feature associations from which we can use 3D geometry to recover the states that we care about. That's effectively what Structure from Motion is doing. If you want to go over this in more detail, I highly recommend looking at Richard Selesky's book. It's available for free online, and I've included the link on this slide. So what bundle adjustment does is it takes this SLAM loop or SLAM problem that we've talked about, and we make it a little bit more specific. We're now talking about recovering the position of camera and the orientation of camera with respect to some map points, and then triangulating further map points using those camera poses. And this process repeats itself over and over. Bundle adjustment is just a form of optimization that does these steps jointly. And there's many different ways to set up a pipeline that does this. We can't go into all of them, but what I'm going to provide here is sort of a high-level simplified pipeline that is representative of a lot of different SLAM problems, I think. The general steps are outlined here. So typically you're going to have some incoming set of frames. They don't have to be sort of temporally coherent, but usually in an embedded application like a real-time system on a drone or on an AR system on a phone, you're going to be getting a sequence of images arriving in time, ordered from a video stream. You're going to compute feature associations. Again, this is the abstraction I was talking about earlier. We're now saying that our sensor, it gives us these images, but we're going to compute unique associations across time where we identify points and track them. And we'll come back to that in a moment and how that's done. Once you have those 2D feature tracks, you then have to do an outlier rejection step. This is just removing data that doesn't agree with your physical model of the world. We'll give some specific examples of that in a moment. And then you often will compute the pose of your platform for the most recent frame. This is sort of a pre-processing step that we need to initialize the bundle adjustment optimization. And then finally, we do the actual optimization itself, which is kind of jointly taking all of those map points and observations and poses and solving for them. So that's very high level, and we'll come back to some of these in a little bit more detail in a second. So first, the abstraction that I mentioned of feature matches. So this is important because we're taking in images. That's the actual thing that our sensor reads. But for the purpose of the optimization, it's convenient to abstract that away and say, given these images, let's back out some unique 2D feature tracks. So what that is an association of a given point in an image over many sequential frames. How do you do this? So there's many different choices. One is to use descriptor matching. At a high level, what descriptor matching does is you compute a unique code or sort of a unique hash for each point in the image using information from the local appearance of that point, and then you can match those codes across frames. So this image on the left kind of illustrates that process. You have these correct associations in green and then incorrect outlier associations in red. But the two images can be taken at very different times of day, very different orientations or view angles, but the association can still work because we've got this descriptor extractor that is looking for unique codes that can be associated across time. This approach is typically moderately expensive compute-wise. It can be hardware accelerated, but it will give you the benefit of operating over wide baselines. Another approach is to use 2D feature tracking, which is what you see in the right here. So this is running on old data from the previous Skydio product, the Skydio R1. You can see these little traces in the gray images. These are 2D feature tracks which are associated over time. And we're using an optical flow style method on this data here. So what that means is we're taking sequential frames and using local information from the image gradients to associate points over time. And these methods have the benefit of being typically pretty fast, but they tend to depend on having a decent initial guess to work reliably, so they don't work on as wide of a baseline. So this graph is very simplified, not meant to be to scale, but it kind of illustrates the trade-off that you're faced with here. You can add more computational cost and get a more expensive descriptor, and it will be more robust in that it will give you more correct associations and fewer incorrect associations. But ultimately, there is an increase in computational cost associated with that. So it's something that you have to consider, and it's going to have implications downstream as well. So what are some real-world examples of outliers? Well, here are some taken from the Skydio drone. So usually your feature association method is making some additional assumptions about the world in order to introduce this kind of convenient abstraction of giving 2D feature tracks. We make additional assumptions like, for instance, that surfaces are ideally Lambertian, or that illumination is relatively consistent across frames, that there aren't totally wild extreme changes in camera contrast or brightness. We might additionally assume that there are locally planar regions about a point, and that we can use those planar regions to track the point. All of these assumptions break down in the real world eventually. These images here are just of some cases where that happened. So for instance, the top middle one here, the appearance between these two images is close, but you can tell they're visually very different because of the way light has refracted through the lens. And that violates the model of the underlying feature tracker. It can't reason about that. And so we're going to get outlier data. And these outliers they're different from noise in that they won't be random. They'll often be correlated with your state. And they certainly won't be nice, convenient Gaussian errors, which is something we'll come back to later. So at a high level, outliers are points that do not agree with your sensor model. How do we deal with them? Well, let's review a particular example here. So I'm going to go over one method. This is a popular method, which is why I choose it, and it's a simple method, but it's not the only method. I should clarify that, but we'll review how it works. So for this problem, we're going to assume we have a simple toy data set where our sensor has given us measurements over time. Those measurements are a linear function of time, and there's two parameters, alpha and beta, that we need to estimate. So if you look at that data set, this is what it looks like. The blue line here is the ground truth model. The green points, the green X's are inlier data, and the red diamonds are the outliers. And as you can see, there's about a 15% outlier fraction here. Now, if you've taken linear algebra, you know at least ignoring the outliers, this problem is very trivial to solve. You just do some linear algebra, you can find a linear fit to the points. But in the presence of outliers, that doesn't really work. And that's what we've done here. This purple dashed line is the fit, just ignoring the outliers. By ignoring, I mean we're just blindly including them naively in our solution. And you can see the slope is wrong and the vertical offset is wrong, so we haven't really recovered the parameters. So one approach to solving this is called random sample consensus, or RANSAC. It's extremely simple. What it consists of is that we're going to iterate, and at each iteration we're going to sample a minimal set of 2 points, fit the line using those 2 points, and then test all the other points against our fit. And once we find that enough points agree with the solution, we'll take that and designate it as the true solution, and that as the true inlier set. So for example, on the first iteration, you might sample these 2 points, one of which is an inlier, one of which is an outlier. Accordingly, the fit is not very good, as you can see. And if we count the number of points that agree, those are the ones now here encircled in black. There's not very many of them. And so it's fairly simple to say, well, this is a very low fraction of the total data that agrees, so this is probably a very poor fit, and we can ignore it. Similarly, you might sample these two inliers, and even though both points are inliers, they've still given us a poor solution. And the reason for that is that we chose 2 points very close to each other on the x-axis, and in the presence of noise, that doesn't give a very good fit for a straight line. So this could be described as sort of a conditioning problem with this particular solution. So typically in a RANSAC implementation, you would have some kind of heuristics to sort of identify these bad solutions and reject them. Although in this case, simply counting the number of inliers also gives us a pretty good sense that this is not the correct solution because a very small number of points agree. So you would reject this as well. And then finally, on some iteration, you'll eventually sample 2 good inliers, and you'll get a fit that is pretty close to the true underlying set of parameters, and consequentially, a lot of the points will tend to agree. And then you can take this inlier set, which is now large, and say we found the true inlier set and fit our model with these points. And there you go, you get a pretty good fit. So now the dashed purple line agrees with the true blue line quite well. If you're astute, you'll notice that we haven't recovered all the inliers. Some of them have not been included. And so algorithms like RANSAC in general don't give you any guarantee that they will find all the inliers. At best, what you'll get is an inlier set, but not necessarily the broadest or the most conclusive or complete inlier set. Second, in this case, we've rejected all the outliers, and that was possible because this is toy data, which has been deliberately selected for ease of demonstration. But that won't always necessarily be possible. Sometimes you'll be able to eliminate all the outliers, and sometimes there may be some that the RANSAC implementation doesn't catch. And so it's typically the case that you will layer multiple sort of outlier rejection algorithms, different heuristics, in order to catch as many of these as you can. So the reason that we chose RANSAC as our example is that it has a lot of things going for it. One, it's dead simple to implement. You just have to implement a while loop where you draw examples randomly, solve a problem, count the inliers, and repeat. So if you have an existing solver, you can easily wrap RANSAC around that solver. You just put it in your loop. It's trivially parallelized. If you have more CPU time or more cores, you can run it in parallel. You can run it for longer, and you'll get a better solution. The downsides are that it has pretty weak guarantees. You'll find a good solution eventually if one exists, but in the presence of high outlier fractions or models that have a lot of parameters, in our case, it was just a toy example of a straight line that had only 2 points required. For a more complicated model, you may require more points. In those cases, it can take quite a long time to converge, but it is still practice, very useful, and has kind of become a mainstay of geometrical computer vision over the years. There's many different variations of it. It appears in different forms, but RANSAC remains a very powerful tool for outlier rejection. So to kind of illustrate the point about how it scales poorly sometimes, what we've plotted here is the number of iterations you would need to draw samples before you find a set free of outliers. And we've plotted that for several different fractions of outliers along the x-axis. And then on the y-axis, you can see the number of iterations that were required. And there's 3 different traces for 3 different example problems that each require 2, 3, and 4 points, respectively. And so this kind of illustrates how, as the outlier fraction increases, or as the number of points you need to draw increases, RANSAC can scale quite unfavorably. And so the exact values aren't that important, but the key takeaway is if there are things you can do to eliminate outliers prior to attempting this kind of algorithm, that may very well be a very good idea because this can scale quite poorly. So usually in this SLAM pipeline, this will fit in here. So after you've gotten your 2D feature associations from your either descriptor matcher or your optical flow-based tracker, you'll run them through some kind of outlier rejection. There's a bunch of different algorithms you can do here, but you typically do that before you do the bundle adjustment optimization. And the reason for that is that if you recall, the RANSAC scales rather poorly in the number of parameters, because as you add more parameters, you need more points to form a minimal set. So a bundle adjustment is optimizing over many, many parameters, many camera poses, many points, and it's doing all of these simultaneously. So if you were to attempt to wrap it in a RANSAC, you would find that the number of minimal points you have to sample is quite high, and so it wouldn't scale very well. So usually the outlier rejection step is done as a pre-processing step prior to the optimization in the SLAM system. So this is a visualization of what bundle adjustment looks like as a factor graph. I've introduced a new piece of notation here, which is this diamond symbol. The diamond just represents a bundle of rays, so all the observations of a given landmark just grouped together to make the graph a little cleaner. You'll note this additional parameter here beside the landmarks and beside the positions of the cameras, which are the blue circles. And that's the camera calibration parameters, which here is the pink circle. So the camera calibrations are things like the lens parameters. What is the lens geometry? What is the focal length? Where is the optical center of the image? Things like that. And these you have to consider because they vary with temperature, they vary from camera to camera, and so typically you would optimize them online as your system runs. One thing to note from this graph, which may not be immediately obvious but should jump out in the factor graph representation, is that there's no direct connection between each successive pose of the camera, the blue circles, that is to say. There's no direct line between those, and that's because the camera does not directly measure any kind of information about its relative pose. Instead, the only way you can get that is to infer it by looking at landmarks. And so while given a set of camera landmarks, you can recover the relative pose between the cameras. Absent any kind of common landmarks or common information between images, you can't. So, yes. Now, we've kind of given an overview of the bundle adjustment problem and how it's set up and how it's formulated. We've discussed the feature association a little bit, but we haven't really talked about how the problem is actually practically solved under the hood. So what we have is some feature measurements. Those are the tracks, which here are represented by the Z, Z1, Z2, Z3, and so on. You have a measurement model that describes the geometry of how those points will appear in the images, given the positions of the cameras and given the landmarks. And then you have this black box that we need to fill in, and that black box is the solver that is going to take this system of nonlinear equations and produce the parameters that we care about. So there's different ways of doing this, and it's going to depend somewhat on your problem. For some problems, there may be specific closed-form solutions. Others maybe not. The general technique, which I'm going to introduce, is called nonlinear least squares. There's many ways to do this. Nonlinear least squares is good in that it's general. It can be applied to a lot of different problems. And it's typically fast. It's relatively easy to implement on an embedded system. If you want a very comprehensive, very detailed overview of how nonlinear least squares exactly solves the SLAM problem, I recommend looking at Tim Barfoot's book, State Estimation for Robotics. Don't let the robotics part dissuade you if you work in a different industry. The techniques described therein are very general. It's really a probabilistic SLAM book, and there's very comprehensive, very detailed derivations in there that will show how this works, and I highly recommend looking at that if you're going to implement a SLAM pipeline yourself. Also, it's available for free online. So we're going to have to make a couple of additional assumptions in order to do this. So we started with we have this set of nonlinear equations that are from our different sensor models. We're going to additionally add another assumption, which is that the noise is zero mean Gaussian, and also that the measurement noise is independent in the sense that each feature track has noise that is independent of the other feature tracks, and that noise is Gaussian. We're also going to have to assume we have some kind of initial guess for our states. That's just a prerequisite of nonlinear least squares. It's an iterative method, and it requires an initial guess. So in a time recursive system, like an online SLAM system, usually this initial guess could be produced from the previous frame. There's a whole kind of area of research into how do you initialize these pipelines when you have no initial guess. And there's quite a lot to go into there that we won't cover today, but know only that you do need an initial guess to apply this method. But that's usually not a blocker, really. So to do this, we're going to take that system of nonlinear measurement models, that system of equations, and we're going to convert them into residual functions, which are basically just the delta between the actual measurement that your sensor gave you, Z, which in the case of a bundle adjustment is just the feature track position in the image, and the predicted location, which our function H gives us, which our sensor model gives us. And then you basically take the sum of squared errors across all these residual functions, and we're going to weight them all by the uncertainty that we attach to each measurement. So you recall we assume the measurements have Gaussian errors. They each have some covariance matrix associated with them, and we're going to weight all of those errors by the inverse of that covariance matrix. And that'll become important later. If you were to simply set all the weights to 1, then this expression would just simplify to the usual squared norm that you see in a normal unweighted nonlinear least squares. So we've set up this problem where we have some parameters, which here we've grouped them all together in some block y. And our best estimate is where we minimize this sum of squared errors, basically. Now, there's a bunch of different reasons why this particular cost function is suitable. It's computationally tractable, and it has some nice probabilistic properties. Again, going into all of them here isn't really feasible. I highly recommend looking at Tim Barfoot's book if you want to kind of understand that in a little bit more detail, but know only that, as it turns out, solving this particular squared cost function is both fairly easy to do and gives you a nice solution that has a probabilistic interpretation to it. Because the function f in general is going to be nonlinear for most SLAM problems, you have to linearize the problem and then solve it iteratively. So by linearize, what we mean is we're taking the first order Taylor expansion of the function using the Jacobian. So we're going to, instead of solving directly for the parameters y, we're going to solve for a perturbation to the parameters y in the tangent space of our original parameters, and then iteratively do this over and over again, adding those little deltas to our estimate as we go. So there are different variations of this. The simplest is Gauss-Newton, which is what I've illustrated here. But there are a few choices that you can try. But in general, at each iteration, the solution is going to look something like this, at least, where you have to take a first-order approximation of the Hessian and invert it. So the reason I highlight that is because the cost of that matrix inversion is cubic, and it scales in the number of parameters that you add to your state. So as you add landmarks, as you add poses, as you add calibration parameters, you are cubically increasing the cost of solving the problem. There's a caveat to that we'll come back to in just a moment, but it's something to be aware of in terms of considering computational cost. The other thing to know is that each residual in this update step is being weighted by the inverse of the uncertainty. So those uncertainties that we have, those are effectively hyperparameters that we can adjust in order to adjust the relative weighting between different measurements or different sensors. So those measurement uncertainties give us a tool for trading off between different sensors if you have a system with many different sensors. And then as a nice byproduct of this, when you linearize about the converged solution, as it turns out, that first order approximation of the Hessian is itself an approximation of the covariance in your estimate. So in addition to getting a solution, you also get a approximate estimate of the uncertainty in that solution. That's a property that can be quite useful if you want to get a sense of how good a particular solution was. So a quick note on sparsity. I just mentioned that the cost of inverting the matrix is cubic. That's not strictly true, though, because in general, SLAM problems can be sparse, or many SLAM problems are sparse. So this is an illustrative toy example where we have these four states, xk minus 3 through xk. They are connected by binary factors, so these are sort of sequential states that have some measurement between them, and then we have a single unary on the start and at the end of the sequence. So in total you have 5 factors here connecting 4 parameters, and if you visualize the Jacobian for that, it's going to have a lot of zeros in it, which are the empty blocks here. And so consequentially, the Hessian, or our approximation of the Hessian, will also be sparse. There's a lot of zeros in that as well. And so when you invert this matrix, you don't necessarily need to refer to every value, and there may be sparsity that you can leverage to do that inversion more quickly. A lot of the time in SLAM or in SLAM research is kind of spent looking at how can we get this sparsity pattern and how do we leverage it in order to solve the system more quickly. So nonlinearly squares at a high level. It takes the problem, puts it into a linearized form, and then in that form, the problem is easy to solve, which is one of the appeals of this approach. You can iteratively apply that approach, and you can kind of weight the different factors that you have by adjusting your measurement noise expressions in order to get more suitable or more desirable trade-offs between your different sensors. There are some caveats. I mean, it can be expensive, but as far as algorithms go, this one is fairly fast and easy to implement on embedded systems. It can be made to run on a fixed memory footprint as well, which is pretty nice for use on embedded systems. And then as a bonus, we can show that with appropriate sort of weights on our measurements, we can achieve an estimate of how uncertain we are. But there are some caveats to that. For one, you need the initial guess for this to work. If that guess is poor, then the optimizer is not going to converge. And in addition, if the guess is poor and the linearization point is poor, then your uncertainty estimate is also effectively kind of meaningless because that covariance depends on having a good linearization point to compute it. And then in order for all this to work, we had to assume Gaussian noise on the measurements. And so the outliers need to be removed because they do not obey or respect that optimization. And even just viewed from an optimization perspective, outliers are going to give incorrect gradients in your optimizer, which are going to point your solution in the wrong direction. So if you'd like to implement a problem like this, you can do it from scratch, but there are some tools available that I recommend referring to or playing around with to learn. So one of the most popular in the research community is GTSAM, which is a package developed by Frank Dellert at Georgia Tech. What's nice about GTSAM is that it allows you to express the problem in factor graph format. So you can just sort of lay out your factor graph in code, give it to the optimizer. It will convert it to a nonlinear least squares problem and solve it for you. And it's kind of built from the ground up for SLAM. So that's a good package to look at. I've included some links to some others here, so you can kind of follow up and look into those if you like. But bundle adjustment implemented in this format as a nonlinear optimization is very useful computationally. It's both very scalable. You can run it on a few frames on a mobile phone or a few frames on a drone. You can run it on tens of thousands of images at city scale. It's straightforward to implement. The caveats are that it only operates at image rate. For example, if your camera is running at 30 frames per second, then at 30 hertz you will get an updated estimate of your pose, which isn't always suitable. In a real-time control application, you will probably want faster than that on a robot, for instance. And then it's also pretty sensitive to outliers, which there's quite a lot of research on this, and quite a lot of compute goes into figuring out how to get rid of outliers as effectively as you can. So one improvement that has really helped to make this technology commercially viable and really useful in the last few years is VIO, or visual inertial odometry. Practically speaking, if you're running bundle adjustment on a real-time system, on an embedded system, if you're doing visual SLAM, it's much easier to do with an IMU in the loop. The trade-off here is there is some integration complexity. You have to add another sensor. You have to synchronize it with your images. There's work involved to do that. It also adds some calibration parameters like the physical transform from the IMU to the camera itself, which I mentioned previously. This is something that you're going to have to consider and include in your model, but it can make the system far, far more robust. And one of the ways that it does that is illustrated here in this factor graph. You can see now there's this horizontal backbone connecting the camera positions and orientations, which again are the blue circles. So previously, the only way to measure the camera location was by observing landmarks that had been seen in another camera image in a conventional bundle adjustment. Now we can also gain some relative information about how the camera is moved between frames by looking at the IMU data and integrating the IMU data. So that provides a whole new constraint in the optimization, which makes it quite a bit more robust and provides quite a lot of information. So VIO really is probably one of the most successful adaptations of vision research in recent years to consumer or industrial markets. It's present in smartphones in the form of AR-Kit, for example, in your iPhone. It's present in Oculus headsets. It's present in drones like the Skydio drone. It's present in autonomous vehicles. And the reason for this success really is that the camera and IMU are highly complementary sensors. The camera has a low update rate, high compute cost, suffers from outlier data. IMU is sort of the opposite of that in every respect. It has a high update rate, it has low compute cost, and there aren't really any outliers in IMU data, barring perhaps IMU saturation, but usually that's not the case. Of course, the issue with the IMU is that it's a very drifty sensor. It has biases that need to be estimated. It has noise, and so it's good over short time intervals, but over time it will drift. The camera is perfectly complementary to that in that it can accurately localize landmarks at long distances, and so it won't drift. And so you can combine these two things together, and it's really sort of a marriage made in heaven, produces a very robust visual SLAM pipeline. One of the key ways in which it helps is at this step of the pipeline, outlier rejection, feature associations. Because the IMU gives you an estimate of your incremental motion between frames, it gives you an estimate of, or gives you an initial guess, I should say, of where feature tracks will be between images. So that initial guess can be very powerful additional assumption that you can use in your feature association method. And additionally, it gives you some initial guess for your outlier rejection algorithm, so you can make that step more robust as well. So as a reference here, I provided some links to existing open source implementations of structure from motion and bundle adjustment. There are some here that are kind of designed for large offline reconstruction, like the Rome example I showed at the start. Call map, for instance, can do that kind of thing. Some of these are real-time SLAM pipelines that use only visual information, like orb SLAM. They can just run on an arbitrary camera sequence, assuming you have a calibrated camera. Or there are some of these that are VIO implementations, like Vin's Mono here, can run on a cell phone or on a drone and give you real-time pose estimates and sparse maps by combining IMU data with visual information. So I highly recommend, if you're thinking of implementing a visual SLAM pipeline, to look at some of these. I've kind of given a very high-level overview here and skipped quite a lot of details to get into the kind of the time slot for this talk, but there are many heuristics and kind of implementation details that potentially matter quite a lot that are worth knowing about. And so these examples are places where you can kind of learn a little bit about some of those. And many of these have corresponding papers, which I also recommend reading. And then last but not least, I have some links here to follow up reading. Again, highly recommend Tim Barfoot's book, State Estimation for Robotics, if you want implementation details or to understand how the nonlinear optimization has a probabilistic interpretation, or understand how it solves the SLAM problem at all. That's a great resource, and it's available for free online. I've also included a link here to a tutorial or a review of visual odometry algorithms written by Davide Scaramuza. That's a great resource. Visual odometry and VIO, again, are probably one of the most successful adaptations of computer vision research to commercialization in the last few years, and so they're worth looking at, I think. And if you have any questions, feel free to reach out to me. My email's on this slide, and if you like SLAM or are interested in SLAM, Skydio has a ton of state estimation and SLAM problems that need to be solved, and we are always looking for talented software engineers. So feel free to drop me a line. Thank you.